Hello and welcome. Today I'm going to be talking about that game, Dragonfire, for the TRS-80 color computer, and the highly advanced techniques that it's using to take advantage of undocumented effects to do some fascinating things, and why it breaks MAME. But this video is about a lot more than that. I'm actually going to be talking about a bug that I discovered in the MAME debugger. Yes, MAME has a debugger. You can debug the emulated machine using the CPU that machine runs on. So if you're emulating a TRS-80 color computer, you have a 6809 debugger, which is super useful for debugging any software that you're running on it, but it can do a lot more than that. You can step through cartridge ROMs. You can step through the built-in ROM of the basic interpreter. You can set watch points on hardware registers so that you can be notified when the video display mode changes. You can even find out exactly where the beam on the CRT is at any given point. Much of this you could never do on the original hardware, so it's super useful. That is until I discovered this bug which made what I was trying to do impossible. So we're going to be talking about the steps I went through to try to understand the problem in MAME and to fix MAME. And along the way, we're going to run into Dragonfire and see if we can get that working better as well. Before you go further, you might want to check out this video, which goes into detail about the field sync interrupts and the horizontal sync interrupt, and talks about how CRT TVs adhered to the NTSC standard and how the beams would go across, things like vertical blanking, horizontal blanking. Some of that's going to be pretty useful a bit later on. And in fact, I'm going to even remind you a little bit later on, like, have you seen this video yet? Because you should probably watch it. If you know it already, you don't have to watch it. But, you know, you might need a refresher. Anyway, let's go. I've been working on taking a game I started in high school and trying to resurrect it and get it to run again, and I was documenting my progress in this playlist. Once I got it functional, I then started to make changes to it, to add some stack blasting and off-screen buffering and stuff. And then when I got to the end of this video, I ran into a bug in MAME, and I had been using MAME to do all of my debugging. So a bug in the MAME debugger would cause problems. Let's take a look. Another nice feature on the debugger is it tells you where the beam on your CRT is. So it tells you the X location and the Y location. I'm expecting the Y location to be at the bottom of the frame every time. Keep your eye on beam Y as I advance to the next frame. It's all over the place. What's going on? Maybe I'm not really even looking at reality. How do I know what I'm seeing? Am I really seeing tearing, or am I just seeing an artifact of some bug in MAME? So this is some of the MAME source code for the MAME debugger. And here you can see it adds the symbols beam X, beam Y, and frame so that you get to view them as part of the debugger window. Where do those values come from? They come from the screen device. So the screen device has an HPause and a VPause function. Let's take a look. VPause just does a bunch of math. It bases its answer simply off of the machine time and other aspects of the screen that it knows it needs to do to help it figure out which scan line it must be on. And HPause does a similar thing for the horizontal position. It's simply some math based on how much time has transpired since the V-blanking has started. Now this screen device is shared by all sorts of video display devices, including the 6847. And it's those display video devices that decide when it's time to issue interrupts, not the screen device. So it's essential that the screen device is perfectly in sync with the video display generator. And this is the code for the 6847, in particular the code where it initializes the screen so it knows how big it is and how fast the refresh needs to go. And you can see stuff here like it takes cases based on whether we're PAL or NTSC. It sets the size, the visible area, meaning the blanking happens outside this area. And it tells the screen device how much V-blanking time there is. This 0 is a little suspicious and was one of the first things I noticed that made me wonder, wait a minute, what's going on here? 0 V-blanking? I don't think so. The 6847 has timers that go off at various points, including every time you reach the end of each horizontal line. When that happens, this function is called to update a few fields, including which physical scan line are we on. Keeping track of that physical scan line is important because it tells us if we're near a field sync or not. And this function decides, oh, it looks like we're right near a field sync needs to go off, and it will adjust the timer when we're at the line just before the field sync. So you have the screen device independently using its clock to decide what to render, and you have the VDG using its own clock to decide where it is in the frame and whether it's time to issue interrupts or not. So it's essential that these parameters are correct. I added some logging to this function so I could actually see for certain exactly where the 6847 believed it was within the field and where the screen device thought it was within the field. And the logging looks a little bit like this. So I'm logging the screen's vertical position along with the 6847's physical scan line and a bunch of other stuff too. And so at the beginning of the log, it looks like screen line 0 is relating to physical scan line 4 from the 6847. And if I keep searching just for that string, now it's associated with physical scan line 3 for that frame, 3 again, 3 again, now it's 2. And if I hold down the search, you'll see from frame to frame, they drift out of sync. So the first thing I needed to do was to really analyze these parameters and see if the screen device really was receiving the correct values. And you'll see there's a comment here that says that these functions are no longer the functions you're supposed to use when initializing the screen device. There's something called set raw, which is now the preferred way to do it. It defines everything in terms of a pixel clock, and you tell it how many pixels on each horizontal line, and when does the blanking end and start, how many vertical lines are there, and when does a vertical blanking end and start. But what's a pixel clock? You're not going to find that in the 6847 datasheet. The pixel clock is the frequency it takes to render a single pixel. The key is to find a multiplier for the VDG clock that will transpire over the course of a single pixel and provide the least, hopefully, 0 amount of round-off error. So how on earth do I figure that out? According to the 6847 datasheet, there are 227.5 cycles per horizontal line. So this is a good number to start with, except for the fact that that's a bad number to start with because it's actually 228 clock cycles. It has become apparent to me that data sheets are not always accurate. And what you really want are people with oscilloscopes and voltmeters and whatever those devices are actually reverse engineering what really goes on in the chips. The original authors of these files did a lot of this experimentation themselves, or they relied on other people who did some of the experimentation. And sure enough, they determined it really is 228, not 227.5 clock cycles. The datasheet also breaks down those cycles into the various portions of the line. For example, front and back porch duration, which is part of the horizontal blanking, the left border, the right border, and also the active video, which comes between the left border and the right border, which they estimate to be 128. Now, this is a number I can get my head around because there are 256 pixels in the active video area. So it looks like if I simply use a multiplier of 2, that should get me the pixel clock that I need. So eventually I came up with this call to replace those original calls to set up the screen, and I'm now multiplying the VDG's clock by 2. That required making sure that I had all the right numbers for everything else, including the number of pixels per horizontal line, So this would account for not just the 256 active video pixels, but how many pixels then would be on the left and the right border and during the blinking period. And then that also included how many horizontal lines per field, and when does the vertical blanking start. And no, it's not 0 lines of vertical blanking anymore. I have to be exactly perfectly in sync. Now when I log each advance to the next scan line, and I look for what happens when the vertical position is 0, the physical scan line stays at 1. So I'm just going to search through this, advancing through the file. There's no longer any drift. I made a lot of mistakes before I got to this point. I don't want to make it look like this was straightforward for me, even though I think it was straightforward, but not for me. I made a lot of different attempts, trying a lot of different approaches before finally I got it like this. But even this was not enough. Even though the debugger now seemed happy and all the field sync interrupts were happening on the same scan line, I just couldn't leave well enough alone, and I had to look at this Dragonfire for myself and see, well, how bad is it really in MAME? Well, it's this bad. Hey there, it's Dave from the future. As I'm editing this together, I just want to add a little clarification. Between the left side and the right side, there's quite a bit of a tint difference between the two. That's not what's at issue. I'm really not sure what's responsible for that. It could very well be that my real CoCo 2, as it goes through my capture system, the colors might be getting munged quite a bit. And it's quite possible that the colors on MAME are more correct. I don't really know. But if you keep your eye on the right side screen, I will point out the actual issues with the mouse. So on the left, you can see this weird, shrinking and growing region of extra purple. And on this side, you can see an extra growing and shrinking region of green and yellow parts of the brick. And if you look carefully in the right border, you'll see this bizarre line that goes up and up and up and up. Then there are these extra purple outlines and yellow outlines in some places. Like, what is going on? In order to understand, we need to understand what this game is trying to do. The CoCos 1 and 2 have several graphics modes that are available, and Dragonfire happens to use this one right here. So you have 128 pixels going across by 192 pixels going down, and each pixel can be one of 4 colors. Those colors are determined by the color set that you chose to use. So if you use color set 0, your colors are green, yellow, blue, and red, and that's it. Each pixel is encoded by 2 bits, and so these 2 bits, 0, 0, give you green, 0, 1 yellow, 1, 0 blue, and 1, 1 red. Here's what those colors look like on real CoCo hardware. You'll see I have this little shaded area just so that you can see the green. Otherwise, you couldn't see the green on top of the green background. And here we have the binary codes that you need to get those different colors. If instead you choose color set 1, those same bit combinations will now give you different colors. You'll get buff, cyan, magenta, or orange. And here's color set 1. If the first color set was like primary colors, this is more like pastels. So again, buff is also the background, so I just have this little shaded area so you can see it. It's kind of like an off-white. Cyan is kind of like a teal. Magenta, is probably purplish, I guess, and you got your orange. The important part here is that the bit sequences to get these colors are exactly the same as the bit sequences to get those primary colors. So there is no way to have one of these colors and one of those other colors on the screen at the same time. It's impossible! But let's take another look at Dragonfire. We've got our primary colors. We have our green, yellow, red, and blue. But dude, that's cyan! And that is buff! And when the dude falls, I think he turns orange. Let's see that. There's a little bit of orange there. And that's a tiny bit of magenta. What? How did they get 8 colors when you're only allowed to have 4 colors? Here's a much simpler version of what Dragonfire is doing. So if you look and see on the screen, all we have are the 4 primary colors. We just have our green, red, blue, and yellow. And even though we're trying to name them something else at the bottom, of course they're not going to be the pastels. They're going to be the green, red, blue, yellow. But watch what happens when I run a little assembly code that does some crazy timing stuff. Whoa! What was that? How did that happen? To understand what's going on, we need to understand what the field sync and horizontal sync interrupts are all about. And I'd recommend you take a look at this video if you haven't seen it yet. The quick summary is that at the end of every single horizontal line, there's an interrupt to the CoCo and you can run some code. At the end of the frame, there's a field sync interrupt, and again, the CoCo lets you run some code. So what if, at the end of each horizontal sync, we changed the video display mode? In general, a safe way to think about it is the whole screen changes. But the beam in your CRT does go at a finite speed. It's not instantaneous, it just goes across. So anything that's already been drawn in one display mode stays that way. And then when you switch the mode, let's say right around here, anything new that gets drawn will be drawn in the new display mode. But as soon as the beam cycles back up to the top again, it's going to continue in that new mode. So you would have to switch it back to the old mode. So very quickly in this demo, we're in the 0 color set and then switch it to the 1 color set and then back to the 0 color set and then switch it back to the 1 color set and then back and forth and back and forth. And since there are 60 fields per second, that means that 120 times per second, we need to change the mode. I have an upcoming video where I'm going to go over the code for this demo in depth, if you're curious how that works. But that's the main idea behind it. But as complicated as that might seem, that is nothing compared to what Dragonfire is doing. That demo just switched the modes twice per field. But take a look at a given horizontal line. We're in color set 1. Oh, now we're at color set 0. Back to color set 1. In one line, we have 3 different modes going on. But what about down here near the moat? Color set 1, color set 0, color set 1, color set 0, color set 1, color set 0, color set 1. Holy crud! How did they do that? They did very, very meticulous timing where they measure the cycles of every single instruction, and they would add garbage instructions just to use up a few cycles so that they would have exactly the right timing to follow the beam as it goes across. And they had to have a game running at the same time. But this was just par for the course for these developers. These were mainly Atari 2600 developers, and they did this stuff all the time because the Atari 2600 forced developers to do crazy timing stuff. I would highly recommend this video about chasing the beam from this channel, which I found to be very informative and really interesting. In fact, this channel has a lot of really cool videos. They don't know me. This is not a paid recommendation or anything, but it really illuminates what kind of cartwheels they had to go through to program for the Atari 2600. So I guess they figured, oh, the CoCo, I could do a little bit of that for the CoCo too. And they ended up making a game that I don't know if anyone else has ever achieved this kind of colors on the CoCo as part of a game. Quite amazing. So that gives us a clue what might be going on in MAME that's causing all these weird purple fringes, yellow fringes, and everything. The timing to change the mode is not quite lining up with the timing of the beam as it's going across. In the MAME implementation of the MC6847, there are constants that tell you information about timing, such as when does the horizontal sync go low, when does it go high, same for the field sync. And in this calculation to determine where we are within a scan line, we have this strange constant here, this -20, that doesn't have any explanation. The work I had done so far got the field sync to happen at a reliable scan line each field, but it didn't really do anything about the calculations within a horizontal line as to when the H-syncs would happen and when the rendering would start. So I figured, what the heck, while I'm at it, let's see if maybe I can tweak some of these values and try to get Dragonfire working a little bit better. An issue is that the builds take a long time. Just linking alone can easily take 20 or 30 minutes. So I hacked in some temporary code to allow me to write some values into the configuration file. So the MAME.ini lets you configure all different kinds of things about MAME. So why not just add my own entries so that I can tweak those values that I just showed you very quickly? I can just change the ini file, rerun MAME, change the ini file, rerun MAME. And maybe I can kind of like arrive at the correct values that Dragonfire expects. So I started tweaking the values, and I took a lot of notes about how the picture changed in relation to the new values that I would pick. And it kind of drove me crazy. There was a lot of trial and error that I went through until eventually I got this. And I declared victory. It's not perfect, but wow, you don't have that weird line going up. You don't have the crazy purple fringes, except like maybe a tiny little flash, or the green and yellow fringes over here, and a little flash. That's it. And yes, there is this weird outline, this magenta on the bottom and this yellow on the, but it didn't look that bad, right? I was like, this is good, and I submitted that pull request. After that pull request was accepted and then merged into MAME and released, and it changed the aspect ratio for the CoCo by elongating it, making it a little bit taller, which I believe is more accurate for the CoCo. It was pointed out to be by Ciaran of XRoar fame that the dragon on the MAME suddenly changed as well, and it was not changed for the better. It did not look correct. Dragon here refers not to Dragonfire, but the coincidentally named Dragon computer from the 1980s, which had an architecture nearly identical to the TRS-80 color computer, but it was designed for use in countries that use the PAL television standard. While he was at it, Ciaran sent to me the tests that he had used on XRoar, written by Stewart, which did very, very meticulous timing tests on the dragon. And I figured, well, maybe as I tried to undo the damage I did on the dragon, maybe I could try to make the dragon a little bit better timing-wise. So these tests run inside the emulator, inside the machine. So I'm running these tests now against Dragon to show you what I saw. So if you run the first batch, sync and frame timing, you have these crazy flashing lines, which you're not supposed to see. What you're supposed to see is a mode change just around this checkerboard. So the checkerboard's supposed to be a little bit brighter and nothing else should change. So that's like the first test of that batch, the second test of that batch, frame sync, a field sync rather, and then it does horizontal sync ones as well, which just goes totally insane and crazy and goodness gracious. And there are a bunch more in here as well, but I was really just trying to focus on that first batch to see if there was any hope I could try to make headway on that. And I noticed several things that could use some changing, like the numbers of scan lines was not quite correct. The clocks that were used on the dragon were not quite correct. The number of scan lines that were added to pad out the field to work on PAL was not quite correct. And then ensuring that those lines are added at the proper location within the field needed to be adjusted too. But after making those changes, that meant that all the tuning that I had done prior to the H-sync on and off and to the horizontal offsets before rendering, those needed to be tweaked again because they were, I guess, tuned to some of the incorrect other parameters. And now that I made those parameters a little better than the other ones, so I more trial and error. I had to going out of my freaking mind trying to get things correct. After applying those changes, now the test looks very stable. So for example, for the FS falling edge, we see only the checkerboard is highlighted in the new mode. Frames a field sync, and then the horizontal sync, only the checkerboard is highlighted. I was pretty excited. Now if I move on to Suite 2, great, nope, great, nope. So not everything, at least it's not flashing wildly. Many of these are not working, but good enough. And then I said, hey, I wonder what happened to Dragonfire as a result of all of these extra changes. So I went back to the CoCo to check out what Dragonfire was looking like. And dude, it's not worse. In fact, that magenta outline at the bottom of the mode is gone. The yellow outline at the top of the mode is gone. It's actually a little bit better. So those tests from Stewart Orchard, which made it so much easier to tune, ended up making this better as well. So thanks for that. But then I realized that the Sockmaster demos on the CoCo 3 also were meticulously timed, and some of my code was interacting with that. What you're seeing here is how it was before me, but after me I had added like some weird additional garbage. I mean, this isn't perfect, but I had made it worse. So I had to go back in and look at the interface between the CoCo 3 code and the 6847, which it was using, even though the CoCo 3 has a gimme, it was still using the 6847 code for the backward compatibility portion of the gimme. And then I had to kind of recover the CoCo 3 to the changes that I had made to the 6847. And eventually I was able to bring things back up to how they were, which is what you're looking at. Which again is not perfect, but it's better than after I had made my initial changes, which certainly made it worse. So at least now it was back to that baseline. Well, that wraps up my adventures with MAME thus far. You've heard me discuss a couple pull requests during the video. The first pull request has been accepted and was released in that version of MAME. And the second pull request is still open at the time of recording. So I will try to update the description later on if and when that does get accepted and released. Thanks for watching.